Good afternoon, everyone. We're going to start. So welcome to the first MITP seminar of the semester. I'm very happy to see you in great numbers. Please keep it up. Note also that normally this seminar takes place on Tuesdays, usually from 1:15 to 2:15. Yeah, today we have the exception. We made an exception for Gopolang because he's visiting all the way from Vancouver, Canada, where he is a faculty in Simon Fraser University. Originally from South Africa, and he's visiting, giving this talk. Please take it away with searching for light accelerated.
Okay, thank you. So this week that I'm the first seminar of the thing, I didn't know it was special. This is good. I didn't know it was special because I was told that not many students come here, so welcome. So as Sam said, I'm an assistant professor at the Simon Fraser University, which is in Vancouver, in Canada. So today I'm going to be talking about searching for light accelerated dark matter. Now, before I start this talk, I want to say that I generally like to interact with my audience. So I'm not going to stand here and talk at you. So I'd like you to ask me questions as I'm talking. So no question is stupid. So ask me questions if there's something that you don't ask. Okay. So in this talk, I'm going to give a brief overview of dark matter. I'm going to talk about the motivation for why we want to consider fast-moving dark matter, what I call accelerated dark matter or boosted dark matter if you want. I'm going to discuss a specific case, which I call boosted dark matter, which is a model of multi-component dark matter. And I'm going to talk specifically about boosted dark matter electron scattering and focus on atomic effects that are really important for us to consider when looking at these kind of signatures. Okay, so many of us have seen this kind of part before, which is a question of what are the constituents of our universe? So the energy density of our universe can be split into three things. The visible matter, which forms about 5% of our universe, is everything that we can see, touch, feel, galaxies, galaxy clusters, stars, all of that stuff. All the beautiful stuff that we see only actually makes up about 5% of our universe. The rest is in a form of matter, which we don't see, which actually makes up about 80% of the matter density in our universe, which is this dark matter. All we know about dark matter is that it interacts with us gravitationally. We know almost nothing else about dark matter beyond that. Then there's also another thing which we call dark energy, which is about 70% of our universe, which the only thing that we know about dark energy is that it's responsible for the universe expanding. And so there's a lot of research that's going on in these two sectors, in which we're trying to find out what is the fundamental physics that governs these sectors. Now, we understand the fundamental physics that governs this sector over here, which is called the standard model of particle physics. So we know electrons, protons, neutrinos, photons, their properties, and these are well explained by the standard model of particle physics. But are they dark electrons, dark photons, dark whatever, that can describe the dark matter sector or the dark energy sector? This is something that we're trying to find. So my research is trying to figure out what is the fundamental physics that governs the dark matter sector. Okay, so how do we know that dark matter exists? What is dark matter? So I'll talk about a little bit about what is dark matter or what we think dark matter is in the next slides. But how do we know that dark matter exists in the first place? So we have a lot of evidence. Most of this evidence is, in fact, all the evidence is governed by gravity. We only have gravitational interactions of dark matter with us, so that we have inference that tells us that dark matter exists out there. So I've only mentioned 6 pieces of evidence here. We have a lot more evidence beyond this. Now, since this is a seminar and I have a limited amount of time, I'm only going to talk about rotation curves. But I have gravitational lensing. I have CMB, early universe cosmology, that tells me that dark matter exists. The galaxy cluster collisions tells me dark matter exists. There's also other evidence from the early universe cosmology that tells us about this. So let's talk about the rotation curves for a second. And the idea of rotation curves is simply the idea of we're using Newton's laws of gravity. And this idea that if I have a galaxy over here, and I take a look at a star at some point, a distance r away from the center of the galaxy, I can calculate its rotational velocity around this, or its rotational force around this galaxy, which is kind of the centripetal force. And I know that it's bound in the structure, so I have a Newton's force of gravity. Now, the fact that this thing rotates around this and just doesn't fall in or go out is there's a balance of forces over here. Now, if I balance those forces, that means I can write the rotational velocity as a function of g times m as function of r over r. Now, if I look at stars from the center of the galaxy going outwards, I can look at their rotational velocity and I can make a plot like this. And this plot here is governed when going up here by the fact that the mass increases. So there's some singularity over here, which we refer to as a black hole. Now, the mass here increases, which dominates this term, but over here, at some point, the mass starts to decrease, and the 1 over square root r starts to drop. And I expect that this plot is going to look something like this. Now, measurements tell me something different. Measurements tell me actually that I do increase like that, but actually stay constant at some point r far away from the center of the galaxy, right? And so this is evidence, this is clear evidence that we have that there's some mass, missing mass that we don't see, that tells us that is there in the atypical galaxy. And so we call this a dark matter halo. So a picture of this would be, here's a typical galaxy, and this is what the dark matter halo would look like. Yeah.
What are those features in the white line? White curve?
This is some data thing. I don't know. I'll be honest, I don't know. Yeah, so different galaxies have different features, and all of them have different. I think this is because they trace the baryonic matter. So essentially what this is that the dark matter line would be somewhere around here. The baryonic line would look exactly like this, but over in here. And when you fit the dark matter plus baryon line, it gives you this feature over here. It actually just traces the baryons, which are the matter in the galaxy. Yeah, so but what those features are, I have no idea. Okay, so essentially what this says is that if I had to look at a galaxy face on, this is what it would look like. So a galaxy, this is how observed galaxies move. So if I had a galaxy that had no dark matter, I can put this in a simulation, and I'll see that a galaxy without any dark matter would move the following way. So I'd have the center rotating much faster than the outer parts of the galaxy, right? But then if I put the same thing but with dark matter in a simulation, I would see something like this, where the center rotates almost as fast as the outer parts of the galaxy. Now, simulation actually ends up matching our data, and what we see is that this kind of gives us an idea of, our intuition of that dark matter exists is actually a real thing and not just in our imagination. All right.
So I don't really know anything about that matter besides that it exists. What does this mean? Does it not follow a spherical distribution or something?
But this doesn't tell me anything about its distribution. This just says the rotational velocity in the galaxy.
But if it were spherically distributed, then I mean it would be. Then it would be the right curve, right? Even
Why?
Dark matter.
No, it wouldn't be, right? Because this. So here I'm looking at the rotational velocity as a function of radius, right? This here, I'm moving much faster at the center than at the outer edges, right?
I think the question is, why doesn't the dark matter sort of cluster in the center of the galaxy as well? Why is it this
Yeah,
big
like
ring?
Why is it a big halo? That's a question I don't know, actually. Do you know?
I guess it doesn't have any additional interactions. It's right. So you only have gravity.
Yeah, I mean that's the question. But I mean, even just with the gravitational interaction, everything would fall inside.
But with the gravitational interaction, so do you?
So it's like with particles orbiting a black hole. You need the viscous friction and the accretion density to get started. So you have something similar here. Don't have any viscous processes of dark matter, so you can maintain a large halo.
So are you thinking that a dark matter halo is, because it's a black hole, there's some singularity there that the dark matter has to be?
No, you're just wondering why it's not as compact.
Why is it not as compact as?
Yeah,
It's purely because of the lack of interactions. It does not have as many interactions with the standard model with itself as the standard model does. So that's simply because of this. And its angular momentum essentially makes it such a puffy thing. Yeah, sorry, I didn't understand your question.
So that's why they call it weakly interactive.
Yeah, it's a weakly interactive massive. Okay, I'll talk about this in a second. I'm not going to be talking about weakly interactive massive particles, but the idea here is that the dark matter is weakly interactive. And so, yeah, so the idea here is that you have this distribution of dark matter. So you could also ask, so people have actually looked at dwarf galaxies, where there is actually a distribution of dark matter in dwarf galaxies, and there was this issue with the cusp versus core problem. So the idea here is that why should I have much more dark matter much more dense in the core than, say, puffily distributed, right? So if I have a core, then the density is much more towards the center. And if I have a cusp, the density is it's more spread out, right? And then people thought about, well, self-interacting dark matter, if dark matter itself interacts much more strongly with each other, then it can scatter off each other and then kind of spread out. But essentially, it's the weak interactions and the angular momentum of the dark matter that is actually causing this ball-like structure.
When you say weakly interacting, it weakly interacts with itself also.
Yes. Okay. So any further questions? All right. Now, an inconvenient truth about dark matter is that if dark matter is a particle, we know almost nothing about it, except the fact that it has gravitational interactions. Right? We don't know what its mass is. We know that it must have we think that there's a range of masses to which it could belong. Can it have spin? Does it decay? We know that it has to be, if it decays, it has to decay in the age of the universe, otherwise structure would not have formed. Right? It cannot be produced and then decay immediately like a Z boson. So is it an elementary particle, or is it a composite state? So people talk about super heavy dark matter that is a composite state. It's composed of a large number of elementary dark matter particles. And so the question then is, the question that I'm trying to figure out is, how do we find these non-gravitational interactions of dark matter? And I talk about a particle, but why particle? Could dark matter be a particle? Should dark matter be a particle? No, we don't. No one says that it should. Right? Can be a particle, could be some continuum state. We don't know. But I'm a particle physicist, so I think about things from the top up, and my research is based on particle physics, so I like to think of things as particles. Right? I'm formed of particles. So. All right. So, and particle dark matter is actually very well motivated, in the sense that there's a large range of possibilities of what dark matter could be.
Sorry, particle dark matter as opposed to what? Isn't everything a particle?
Well, you could have continuum dark matter.
Oh, right. But black holes would be like standard matter. I mean, some fields would collapse to form black holes. All fields would have particles.
So if I have a conformal field theory, the dark matter could be a continuum. It doesn't have to be a localized particle. When I say a particle, I'm talking about some localized state.
In massive particle as
Yeah.
opposed to massless particles.
Yes. Yeah. And here, by the way, when I'm talking about this ultralight regime, essentially here I'm talking about it as something that has a really long Broglie wavelength. And it's not necessarily strictly speaking a particle, but a wave. But I still refer to it as a particle.
So yeah, that's essentially a massless particle.
Yeah. Yeah, but it's not really massless. That's not mass.
There is modified.
Yeah.
Yeah, so I'm not going to talk about that here, but essentially the modified Newtonian dynamics says that at the scale of the galaxies that I told you about, essentially you could say, well, I don't really care about dark matter. Dark matter doesn't exist. What I need to do is just modify gravity. I modify Newton's laws, and I can fit the data much better than the dark matter fit can. Now that can work at the scale of galaxies. Now, what happens when I go to galaxy clusters when I need general relativity? I can't modify general relativity in the same way that I can at the Newton's gravity. What happens when I go to cosmology, the larger scales? I still need general relativity. I can't actually fit the data very well with modified gravity. And so that's one of the problems of that here. But yeah, I'm gonna talk about that. Talk about that.
Do you consider axial WIMPs?
No. I mean, it depends on what you mean by WIMPs. right? When we talk about weakly interacting massive particles, essentially, I'm going to define what I mean by a WIMP here. Essentially, I mean a particle that interacts weakly, like through the weak force with the standard model. And also it's massive. What is massive? Massive is what 1 GeV to 100 TeV. And so axions really don't interact. Yeah, they interact weakly, but not through the weak force. So different people have different definitions of WIMPs. Okay, so we have this whole range of parameters of ideas of what dark matter could be. So we have sub-GeV dark matter, which is dark matter that is lighter than a proton in mass, but heavier than an electron. I can go all the way to ultra heavy, which is beyond 100 TeV, and even heavier than that in something called the primordial black hole, which has also itself a large range of masses. And a primordial black hole is just a black hole, a tiny black hole that was formed when the universe was formed. Okay, so for the past decades, we've been focusing on this region of parameter space called WIMPs. And there are a lot of theoretical motivations for this. I'm not going to talk about those, but we've been focusing on this because we thought that this is the natural dark matter candidate. We thought that if we turn on the LHC, these guys are just going to come popping out and saying, hello, we're here. But they actually haven't. We thought that if I look at the galactic center and annihilate these particles, they're just going to show up in terms of standard model. We haven't seen them. There's direct detection, where I put a detector deep underground and wait for dark matter particles to come scatter inside my detector and form cause a nuclear recoil. We thought that the moment these experiments come online, that these are going to just pop out. We haven't seen any of it, right? And so we've been searching for this for a really long time. So we've been searching in direct detection, as I mentioned, scattering. We've been looking at indirect detection, and also we've been looking at collider constraints, mostly the Large Hadron Collider. And all of these searches are complementary in the sense that, let's say I found a dark matter using direct detection. I wouldn't actually necessarily know that it's a dark matter particle unless I went and I found the same particle at a collider. Because at a collider, I have more control, right? I know what energy I'm putting into a collision. I know the energy that should be coming out, so I have a little bit more control over what's happening in that environment. So I should be able to see the exact same particle there. Now, it's not surprising that we haven't found anything in all these searches. Okay. Now, instead of saying that the WIMPs are ruled out, I say that they're heavily constrained. My heavily constrained is that we haven't seen anything. The parameter space of WIMPs is actually closing down quite a bit. What do I mean by this? Let's look at the status of direct detection, dark matter direct detection. So think of direct detection as kind of like a billiard ball scattering. So how many of you play snooker? Billiard balls. Raise your hand. Okay. So I have a cue ball that hits another ball and that ball scatters, right? Imagine that now I'm doing this in a really, really big detector made of like liquid xenon or liquid argon or whatever. I'm just not there. This particle comes in, goes through my detector, through the walls of the detector, hits a nucleus and causes this nucleus to scatter. I have some electronics on the walls of this detector that can read off that interaction of the nucleus. And I can kinematically reconstruct this. Remember momentum conservation, energy conservation. I can kinematically reconstruct that to find what is the dark matter particle that came in, or some of the properties of that particle. I can then plot the dark matter nucleus scattering cross-section, which is essentially an idea of area or probability. What is the probability that a dark matter particle comes in and hits a nucleus inside this detector as a function of the dark matter mass? All of these experiments, all these lines here represent different experiments that have been running for the past 2 decades. Okay, all these experiments, they actually represent different materials that were put over, run over different times, and they have different masses. So here I have a 10 kilogram SPC. I forgot what SPC is. Dark side is a liquid argon detector. Deep 3600 is a liquid argon detector. I have xenon 1 ton, which is a liquid xenon detector. And so I put this over a certain amount of time. It's a ton of liquid xenon. And I wait for a dark matter particle to come in, say, over a year. If I don't see anything, I plot this gray region over here, which says that the parameter space above this is ruled out. The area above this actually represents the higher probability. So the further I go up is the higher probability of detecting a dark matter particle. The lower is the lower probability of detecting. Yeah.
Is the scale of the
So this is just the, so here I'm saying centimeter squared, I can convert that into picobars. So 1 picobar is 10 to the minus 36, 10 to the minus 30, no, 35 square centimeters. Bar is 10 to the minus 24 square centimeters. Yeah. And so what I'm saying is that if a dark matter particle was here, actually this experiment would have seen it. Now it hasn't been seen, so we rule out this region, this parameter space. The white regions are still available. Essentially, a dark matter particle could be over here, and these experiments can probe that dark matter particle. What happens over here is what we call a neutrino fog. Essentially, when we are in here, the dark matter or neutrinos can come into the same detector, neutrinos that are produced by the sun, by the atmosphere, by distant supernovae, can come into the detector and cause the same nuclear recoil signal as a dark matter. And I will not be able to tell the difference. Okay, and so in this region here, we have to start thinking about different ways of detecting dark matter. And one interesting way that people have been talking about is directional detection. So being able to distinguish that dark matter is coming from away from the sun, and neutrinos that are coming from the sun are coming from this direction. And so I should be able to tell the direction in which the dark matter is coming from by just looking at nuclear recoils. Right. Now, I say that this is squeezed, as you can see that there's still a little parameter space that is available for me to do a traditional search. And so we're kind of compelled to look at beyond the WIMP. And I've defined the WIMP, remember, as something that is weakly interacting, interacts through a weak force, and is massive, mass above 1 GeV. And so I can look at lower masses. So if I look at lower masses over here, essentially, and this is an old plot, but it hasn't changed by much. So I can look at the same cross-section and now go below a GeV in mass. And those experiments now are no longer as sensitive. Now this whole parameter space opens up. This is that neutrino fog or neutrino flow area again. And so the question is, who or what lives here? And how can we find the dark matter that lives there? What are the opportunities for us to look for dark matter in this case? And so I'm going to be talking about low mass or sub-GeV dark matter searches, just below GeV. These are complementary to WIMP searches. So we're not replacing WIMP searches, we're just saying, while we're doing this parallel, let's just do this, right? And they're very well motivated in the sense that now this new dark matter must interact with me through a new force. It cannot interact through the spanner model Z, the Higgs, or the W force. It has to be a new force, right? If it interacted with the standard model forces, these are really, really large. The cross sections would be really, really tiny. I will not be able to see those. So in order for me to have any hope of seeing these, there must be some new force which is also quite light. Now, this new force has implications in the sense that if I find this interaction with some new force, then essentially this could help me probe how dark matter was produced earlier in the universe. And one way to do this is an idea of called thermal freeze-out, where essentially I'm taking this plot and I'm plotting it, I'm like turning it onto its side, and I have dark matter annihilating into standard model through some new thing, through some new force, and interacts into converts into the standard model. And what I'm doing then is I'm matching what cosmology tells me the amount of dark matter in our universe, and I'm matching that process to the number, which is what we call the relative density. Okay. And so we can also do a process which we call freezing, which is the other way, where I'm annihilating standard model particles into dark matter and populating the relative density early on in the universe. And there are many other things that I can probe using this. And I can do this at a direct detection experiment without actually going to the early universe, without looking at a cosmology experiment. Okay, and I'll show you how we can do that. Now,
sorry, this new force, is it not abelian?
doesn't have to be.
The Z primes have more or less been ruled out for the abelian sector, right? I would see bounds are very strict on Z primes.
Not for sub-GeV dark matter. So
Not
a
for
Z
sub-GeV.
prime, a Z prime cannot be, it's not probed, we cannot probe it at the helix because it's too heavy. So if it's a Z prime, it has to be like, yeah, then that is not ruled out. It's constrained, but it's not. And in fact, for the mass ranges that I'm considering, beamed up experiments actually have been looking for these, and there's still a lot of parameter space to play. So I don't know what mass C primes you're thinking.
I don't know.
Okay. Yeah. I don't know much about anything heavier than they
I'm just curious. I don't know.
Yes. Okay. So the big question is, why do these nuclear recoil experiments not see sub GeV dark matter? Well, the reason is simple: is that the light dark matter is quite visible. So essentially, what I'm asking is, why do these cut off here around 1 GeV? The reason is that these nuclear recoil experiments have a threshold. So when a dark matter or a particle hits a nucleus and causes it to recoil, there's an energy that it comes out. And there's a cut that these experiments put, which is around the keV in energy. Anything below that is thrown out because of all the different backgrounds. And essentially, I can calculate that the recoil energy that is caused by a galactic dark matter. So this is dark matter that is non-relativistic, that forms part of our halo. It's moving at about 10 to the minus 3 times the speed of light, or roughly 220 kilometers per second. I can calculate the nuclear recoil energy as just the reduced mass, the velocity of the dark matter squared over the mass of the nucleus. And what I find is that if I have a 500 MeV dark matter hitting a xenon nucleus, which is roughly 100 GeV, I get about 2.5 EV of energy. It's like a ping pong ball hitting a bowling ball. It's going to be recoil, I'm just not going to see it, right? And so this is well below the keV recoil energies that are required by those experiments, and this is why we have that cut. Now, to probe these lower masses, either I have to reduce find a way to deal with these backgrounds, or look somewhere else. And the other way that I can look is to remember that an atom is a nucleus and electrons around. So if I have a 500 MeV particle, instead of hitting a nucleus, I can hit an electron, which is much, much lighter, right? Now I'm turning the problem on its head and saying, instead of a ping pong ball hitting a bowling ball, I have a bowling ball hitting a ping pong. Okay.
Is that cross section not proportionally smaller?
Why would it be? Electrons are smaller, but this is actually the reduced causes the reduced mass. So why I don't see why the cross section.
And just because the electrons are smaller and the nucleus is very big, the probability of hitting the electron should be maybe smaller, and there are more electrons also.
But the dark matter is quite huge compared to the electron. So the cross section. So if I thought about it as areas, essentially I'm thinking about the electron being smaller than the dark matter's area. Yeah. So and you can ask, what is the probability of hitting a nuclear compared to hitting an electron? Okay, you can calculate that. But that's a fair point, really. It's really a fair point. This is a normal people too.
Yeah. Not asking anyway. I just have a question. Important for me to careful to let's say someone's feelings. I should be able to feel the same feelings as that person. If I'm just having, because you're looking at that meta fiction, right? So, and we haven't been able to take this stuff, and so we've just been able to say that it exists based on the simulation of the universe that we look at. So, how can we design something that could take something that we are not?
I understand your question. It's not physics. It's actual physics. Gravity is physics. I jump, I come back. It's gravity, right? So we detect the dark matter not from simulation, but from gravity. So a gravitational interaction that we have, we know that it's there. It's undeniable that it's there. It's not speculation. Like, so what I was showing with the simulation is just basically our theoretical modeling of saying, do we understand actually what is going on here? So when I put that in the simulation and I compare that to data, it has to match. If it doesn't match, then you're right, it's physics, right? So what the fact that it matches tells us that there is something there.
So what we are trying to identify is what the nature is.
Yes, exactly.
And
what is the nature?
So what I'm saying is that if we are not that nature, how are we able to take a nature that we are not?
That's a good question. How are we able to detect some? Do we actually? That's a good question. Do we actually know that dark matter can interact with us, right? We don't. And there are people like over lunch, we were talking about this idea that you have dark sectors that interact only through gravity. That's actually a really good way of looking for dark matter because we know that it has gravitational interactions, right? So we can construct some other experiments parallel to these ones that say, look, I can go and look for dark matter gravitation. The problem, my feelings is that the problem is it's hard to determine exactly what the dark matter is if it's only interacting gravitation. You can't determine what its spin is. You can't determine what its mass is. Maybe you could within some range, but it's really, really hard because gravity is so weak compared to like electromagnetism or any other force that it's hard.
So at the moment, right, how are we able to, what's the instrumentation or calculation or whatever that we use to determine gravitation, and we do it for calculation based on the mass that we have of things that we know, or we can measure it directly. Measure gravitational energy directly or indirectly.
So we have both calculations and measurements. So we have general relativity, which tells us it's a theory of gravity. So we measured, so we're still testing gravity, general relativity, but we also have things called gravitational waves, which actually kind of confirmed Einstein's theory of gravity. So we have both those things. But yeah, so if you have any further questions, I'm going to continue now, otherwise we're going to run over time. Okay, so one of the things that we look at is dark matter electron scattering, which is that, you know, I'm instead of hitting a nucleus, I'm hitting an electron, and I can look at both large volume noble liquids like argon, xenon, detectors like these really big experiments, or I can look at these small scale tabletop experiments that can look for these light dark matter particles. And in fact, there's an experiment called Sensei that has been running for a while, and it's actually the brainchild of Ruben Essig, who was an undergrad here at Wits. And so when I talked about that I can probe certain methods of dark matter production. Here's a Friesen mechanism here. This is the relic density that's got from Friesen. And if I look at the dark matter electron scattering cross-section, essentially I could have an experiment that is sensitive enough to reach this Friesen region. That says that if that experiment detects dark matter, it's most likely here, and it must be produced in the early universe through some Friesen mechanism. That tells me a lot about the model. It tells me about the dark matter itself. It tells me about the new force that I'm interacting with. Now it's my job to go and look at a collider to go and find that same particle. All right. Now, I told you one way to maximize my energy transfer to the target. The other way is I don't need to go to smaller targets. I can actually just increase the speed of the dark matter. Now, my analogy with a ping pong ball and a bowling ball doesn't actually work anymore, because if I have a bowling ball and I just make it really fast, it's just going to bounce back, right? It's like a ping pong ball hitting a wall. You're not going to move it. But imagine now I have a tennis ball, and it's now moving really fast. It hits the bowling ball is going to, and I'm going to detect this motion. And so instead of looking at dark matter that is moving at 10 to the minus 3 times the speed of light, I'm looking at dark matter that is 0.1 times the speed of light. Okay, and here I have a back of the envelope calculation tells me that a 15 keV recoil this can give a 50 keV recoil and about a 2 MeV electron recoil. Remember that the thresholds that were set by those experiments were about a keV. So now 50 keV is well above those, and 2 MeV is also well above those thresholds. Not only that, it's also above the thresholds that are set by really large volume neutrino experiments. The experiments that are running deep underground that look for these light standard model particles called neutrinos, right? And these by nature have to be really big because neutrinos are also very weakly interacting. And so now we've extended our program to not only search in direct detection experiments, now we're going to neutrino experiments to look for these particles. Okay, now this is where you stop me and say, but hold on. Going back to your question, if I have a dark matter that is forming my halo, right? We know the Earth's escape velocity, right? To the students, what is the Earth's escape velocity? Come on, I did my undergraduate in like long time ago. You should know the Earth's escape velocity. 11.2 kilometers per second, right? So I know that there's an escape velocity, meaning that everything that goes above escape, above 11.2 kilometers per second, is just going to fly off. So if I have a dark matter that is moving really, really fast, then it cannot be part of my halo, right? So then you're telling me that dark matter cannot be part of this halo, right? That tells us something. It infers that if I have any fast-moving dark matter particle, it has to be a subcomponent, meaning that most of my dark matter has to be non-relativistic, but I have this really small subcomponent that is relativistic. And that is another way that we can look for dark matter, through this relativistic motion. How do I produce dark matter relativistically? There are many ways. There's something we call cosmic ray upscattered dark matter, where I have a cosmic ray that is produced by some structure somewhere far away. This cosmic ray propagates, comes towards the Earth, it finds on its way, finds a dark matter particle, it's minding its own business. It hits this dark matter particle. The dark matter particle gets a lot of energy, comes to the detector, and deposits a lot of energy that way. Okay, and here, as you can see, I can go to much lower masses. So I can go to about a keV in mass. And I'm using now experiments beyond direct detection. So this is direct detection experiments. These are neutrino experiments. So I can look for this in neutrino experiments, whereas for non-relativistic dark matter, I cannot do the same thing. Because those experiments are so high thresholds, are so high in threshold that these dark matter particles that are moving really, really slow, they give off a signal, but it's well below the threshold. So those experiments are just going to throw it out. Okay. But now they can't throw out that signal because it's well within their signal, what they're looking for. And so now the question is, how do I distinguish between a neutrino and a fast-moving dark matter? That's still a question of research. We haven't figured that out.
How much of this is model dependent?
Yeah, I'll show you that it actually is model.
Doesn't the fact that we assume that most of this dark matter is halo, non-relativistic. Doesn't the fact that now something has to first be hit by a cosmic ray and then has to be observed produce the cross section?
Exactly. This is why. So you have to look at, when you're calculating this, you have to calculate the flux of the dark matter that is produced. So we assume that all the dark matter that it comes to the detector has actually been accelerated by the cosmic rays. You know, and the correct way to model it would be to say, I have actually angular angles of scattering. So if the dark matter is sitting here, this cosmic ray could come in here and have some impact parameter and just fly off. The dark matter could go that way while the Earth is here, right? We're just assuming that the dark matter is coming in, hits it head on, and causes it to speed up.
The cosmic ray.
Yeah, the cosmic ray. And really, if you think about it, it's kind of like the conservative assumption, because we're assuming that most of the flux comes this way, and therefore we can rule out the dark matter. So we're kind of shooting ourselves in the foot by doing it, essentially. Anyway, so this here is the dark matter nucleus scattering, and this is dark matter electron scattering. And I can look at different experiments like Super Kamikande for that type of search. Here, my collaborators and I looked at a different experiment called Ice Cube, which is in the South Pole, which is really, really big. And what we looked at was looking at the cosmic ray spectrum again. And here I have a dark matter electron scattering when I have a scalar mediator, and this is where the model dependence comes in. So if I have a scalar mediator, I have these limits over here. If I have a vector mediator, the limits actually shrink, and I don't do much better than the current bounds on this. Okay. And so in particle physics, or in particle dark matter phenomenology, essentially what we're doing is we're trying to ask the question, can this experiment see the signal? If it can't see the signal, then we put a bound on it. And all of these are just different bounds of these experiments that have not seen signal. Now, you could say, but that's negative. Why should I set out to go and search for negative results? These negative results actually tell us a lot about the dark matter parameter space. So if I have a model that says dark matter is a fermion, this new force is a scalar, or it's a vector, right? This tells me where the dark matter is not. This is where the dark matter is not. It could be here somewhere. So in the future, I have to go and search over here. Okay, and so if I look at dark matter nucleon scattering, the calculation is a lot more complicated rather than the free scattering. And so I look at a scalar mediator and a vector mediator, and these are the different things here. And the thing to take away from here is that actually the vector mediator does much better in this region. All right. There are different ways that I can look for dark matter, for this accelerated dark matter. I can look at neutrino accelerated dark matter. I know that the sun produces a lot of neutrinos. So if the sun hits neutrinos that are coming from the sun, hits a dark matter on its way, I can look at the velocity, calculate the velocity of the dark matter, which is related to the energy of the neutrino after it escapes the sun, and the mass of the dark matter. And here I'm looking at the flux of the dark matter particles as a function of their velocity. And you see here, this is the non-relativistic dark matter in our halo, and this is the dark matter that has been sped up by neutrinos. And you can see here that this is it's a small subcomponent of this guy over here, even though these guys are actually moving much faster. So it goes well with our intuition that what we were thinking. In an experiment, I'm more likely to see this guy, but in principle, this guy cannot go into a neutrino experiment, but this guy can. So essentially, I'm just widening my search criteria. Okay, and then many other ideas here of like cosmic neutrinos. So these are neutrinos that were produced early in the universe that are traveling to us right now. There's also diffuse supernova neutrino background. This is neutrinos from all the supernova that have ever exploded in the universe, ever. And we're all looking at the background of all of those and looking at the signal from those. I can have dark matter accelerated from evaporating primordial black holes. If I have a black hole sitting there, it evaporates, there's a chance that there might be a dark matter in there that just comes out really, really fast. Or I can have neutrinos from the same thing. The other idea is that I could have a supernova, a star that's about to go supernova. I have a dark matter halo around it. The star blows up, goes supernova. There's shock waves that come from that blowing up, and that can speed up the dark matter that way. So as you can see, part of being in particle theory, particle phenomenology is being creative. So all of these are really creative ideas, and we find ways to go and search it. Okay, so a different mechanism, which is something that I'm working on, which doesn't really depend on so a lot of the stuff like you mentioned really depends on some accelerating mechanism. I have a cosmic ray that I have to first have a cosmic ray, and it interacts with the dark matter. Then I have some acceleration. I first have to have a neutrino that interacts with the dark matter, and I have acceleration. All those depend on those things, but it's essentially, if I thought outside the box a little bit and think about the idea that the dark sector may be non-minimum, i.e. there might be more than one dark sector particle out there. The standard model is non-minimum. We have electrons, photons, muons, neutrinos. They're all stable. So why should we expect that there's only one stable dark matter particle? There could be more than one stable particle. The question then is, how do you stabilize all these different dark matter particles? It's a question of theorists. We build a model that where all these particles are stable. Now, the acceleration factor can come from different sources. For example, if I have this assisted freeze-on mechanism, where I have a heavy dark matter particle, say a chi, I'm going to call this a chi2, which is heavier than chi1, it can annihilate into chi1. The chi1 will always come out at a boost. I could have semi-annihilation, it's a similar type of thing. I could have decay. Those are similar mechanisms. Now I'm going to talk about boosted dark matter, which is the concept that I talked about, where I have a particle A and a particle B. A is heavier than B. And let's imagine that I have some sort of stabilization mechanisms for those U1 prime plus U1 double prime.
I have two questions. In the previous slide, you say small fraction of dark matter could never be reduced. What do you mean by that? I mean, by that being a generic feature.
It's a generic feature of the model in the sense that from exactly this. So if I have a model of a two-component dark matter, and I have this mechanism over here, then a small fraction of this is going to come out relativistic. Because not all the dark matter is going to annihilate. Right?
Masses are different.
Yeah, as long as the masses are different. That's the main point.
And the other is a more big question. I mean, if you say that there can be more dark matter particles, more than one species of dark matter particles, then there can be like a dark SU2 or a dark SU3 sector.
Yeah,
and
exactly.
there can be an entire dark standard model.
There could be a whole mirror sector. In fact, people are looking at mirror sectors as well. So you have an SU3 plus SU2 cross U1 have charge in the standard model. There's a U1 dark, SU2 dark, SU3 dark.
It just need not be the standard model, right? It can be any gauge group.
It can be any gauge group. Yeah, there is a mirror sector that people are.
Those possibilities are everything.
Yeah, people are working on those. I don't know what the current constraints in those are because I don't know.
Yeah, yes.
But you could imagine that maybe the two U1 groups actually interact with each other. So there's some sort of mixing between U1 hypercharge and the U1 dark.
Why would that be very big?
Why?
What would you expect?
Why not?
Why not?
It's a renormalizable coupling in the standard model.
Why would you expect this data?
So what do you mean?
Well, I mean, I would say the simplest minimal example is supersymmetry relativity. And it avoids these issues completely.
What issues?
I mean, issues of hidden sectors. You have the ninth LSP candidate with just SUSY breaking. So, why go through these, Baroque epicycles rather simple field theory explanation?
But isn't supersymmetry and dark sector something?
I wouldn't say so, no.
We haven't seen supersymmetry. It's not part of the standard model.
I agree with that. But I would say it's more minimal explanation than these Baroque ideas of hidden sectors.
I think it's a different case.
It's,
I think it's a different case. I actually disagree. I'm not sure that it's a minimal thing. It's a minimal thing that explains all the theoretical stuff, but in terms of minimal dark sector, it's not. Right? You have to have a whole range of particles that are in the dark sector. Here I'm talking about one particle. Right? There could be another sector state of particles, but I don't care about all those. I only care about one. Yeah. So I think I don't disagrry with you about the supersymmetry. I just disagree about the minimalism.
I guess it's a matter of taste.
Yeah, I think so. Yeah. So there's so many different theories that people work on. That's the gist of all of this. Anyway, so did I answer your question? All right. So here the idea is that I have some galactic dark matter that is moving non-relativistically. I have some really fast candidate that this annihilates directly interacts with this fast dark matter particle, and it's only fast because it comes from this annihilation. In principle, if it doesn't come from this annihilation, then this particle is also quite slow. It's not relativist. So it doesn't interact directly with the standard model, otherwise it would be a WIMP, and we have problems with WIMPs as we've seen. So it interacts with the standard model through this interaction over here. Now, some people, and you could say, well, this is another ad hoc model. Why do I need this? Right? It's just another way that we look at looking for signatures of dark. So there's a way in particle theory, you can look at things from the top down, or from the bottom up. And there are two different ways of looking at the same problem, essentially. Okay. And so essentially I can look at this annihilation into B's, and I'm going to have some sort of contact interaction. And this boost factor comes from the ratio of the MA over MB. And I have the dark matter comes in, the boosted dark matter comes in, interacts with electrons through some new force, as we've seen, similar to a direct detection signal. So I can look at many different areas, like for example, in the galactic center. The galactic center is really huge from where we are. So I'm going to have a cut of cone, a 10-degree cone of the galactic center. And for 20 GeV WIMP dark matter, that annihilates into boosted Bs, I'm going to have this really tiny flux. Now, it's not the end of the world. Even though I have a tiny flux, these particles are moving really, really fast. They're moving almost like neutrinos. So I should still be able to see them in these really huge experiments. And so in a paper that we wrote quite a while ago, we looked at these kind of signals where I have the signal number of events is given as the flux that I calculated before, and some differential scattering cross-section with electrons. And I'm going to look at a simple signal over square root background estimation. And this is what I get. So this is actually setting the sensitivities of all these experiments, where I'm looking at the scattering cross-section of the B's with the standard model as a function of the maximum energy that I expect inside my detector. And so I see here that all these different experiments, so the point of this plot was to see which part of the parameter space these experiments are most sensitive to. This region of parameter space here, the super K, the super Kamiokande experiment actually did the search, and they didn't see a signal. But then with a more dedicated search and more observation time, they actually could reach this region of parameter space. And in principle, this dark matter could be lying over here. And in this plot, I could ask the same question, but differently. how sensitive are these experiments if I plot MA as a function of MP? And here I'm asking the question, how sensitive, whatever the sensitivity lies within this these contours over here.
So what dark matter are we looking at? What model of dark matter?
So this is fermion dark matter with a vector medium. Yeah, sorry, I didn't mention that. And so here I'm talking about epsilon. That epsilon is actually this kinetic mixing between some U1 hypercharged and so U1 dark. And I don't actually extend that. I'm just extending that all the way to only a U1.
Is there a natural point you've got to push these limits to find the relative cross section?
Yeah, so in this case here, we didn't actually fit this, but I don't show this. There's a fit that you can do with the data, and I think it's somewhere around here, but I don't want to say that exactly. Yeah, you can fit the data and say, well, dark matter is actually most naturally over this. I can also look for boosted dark matter from the sun. So essentially, I'm playing the same game, but now I'm looking at a more compact object that is closer to us, which is the sun. And here, the evolution of the sun from when it was born until now, essentially I could have a dark matter particle thermalizing inside the sun. By that I mean a dark matter particle comes in, hits the nucleus inside the sun, and loses energy. And as it loses energy, it just sinks to the center. Okay, and it thermalizes with the other standard model particles inside the sun. I have another dark matter particle coming in, and so therefore they evolve and they keep capturing it. And now I have a whole population of dark matter particles inside the sun. Okay, so now I have a core of these particles that are trapped inside the sun. Now the difference with a galaxy, where I have this puffy thing, compared to a sun, where it's like at the center of the core, is that here I'm assuming that these particles are really heavy. And them being heavy means that they're going to just always just go towards the center. And they're also being kept in the center by the pressure, the gravitational pressure of the sun. Okay, maybe I didn't put that. Anyway, I think you see my point. And now, if I have these particles that are like, I have this, imagine this glob of dark matter in the sun now, these particles now are so close to each other that they annihilate, they find each other, they annihilate into boosted particles. And there's a simple differential equation that I can solve to look at this evolution. So evolution is given by where I calculate the number density of these dark matter particles as a function of time. And this CC here is the capture rate. So the idea that dark matter is coming in, scattering with the standard model, and getting captured. I have the capture rate due to self-interaction. Dark matter comes in, hits another dark matter particle, gets captured. I have evaporation. The dark matter comes in, hits a standard model particle, and just gains energy. Instead of losing energy, it gains energy and just flies off beyond the escape velocity. All right, and I have the same thing with the self-interactions. So the point of here is showing what is the importance of self-interactions. And this is something that was overlooked before in the literature. Here, what we're looking at is that if I have no self-interaction versus if I have minimum and maximum self-interaction, this is what I do. Now, what is minimum and maximum self-interaction? This is actually, again, to the question, this is the observations from astrophysics tell us about the self-interactions of the dark. So if I look at the kinematics of dwarf galaxies, dwarf spheroidal galaxies, the way they interact, tells me that dark matter does not interact with each other very well. I can also look at the bullet cluster of galaxies, and the interactions affected the bullet cluster were two clusters that literally went through each other. And the halos, the dark matter halos, essentially were not perturbed. That gives us how strongly these interactions gives me a maximum value for these self-interactions. My self-interactions, essentially, I just mean the self-scattering of the dark matter particles. So dark matter comes in, scatters with itself through some velocity interaction. Okay. And so if I look at those, essentially I can play the same game again, and you can see that the sensitivity increases because my flux of the dark matter from the sun increases. Okay, so I'm not going to talk too much about these. These are actually more model dependent bounds from the cosmic microwave background. And there's a dark matter experiment called DAMIC, which looks at these. So these are model dependent bounds that I put over here. But essentially what you should pay attention to is that the most sensitive experiments to look for these particles are actually the Dune 40 kiloton experiments. So Dune is a really large liquid argon experiment that is being built at Fermi Lab in the USA. And it's going to basically look for neutrinos. And essentially what we're saying here is that you don't only have to look for neutrinos, you can look for these particles as well. So I'm going to move over and talk about direct detection. And I'm going to speed up because I think I'm running out of time. So in a direct detection experiment, so these particles here are really, really fast moving. These are relativistic particles. In order for them to surpass the energy thresholds of these detectors, they have to be really, really fast. Now, if I go to lower thresholds, like in a direct detection experiment, I'm going to consider somewhat semi-relativistic particles. I'm no longer that super, super fast. Now I'm sort of fast. So there are three regimes, right? I'm like really slow, dark matter, like the ones we have in our halo. I have a bit faster, and then I have super fast dark matter. So for a neutrino experiment, I need really, really fast dark matter. For a dark matter direct detection experiment, I need semi-fast. And then for dark matter direct detection experiment, again, for WIMPs, I need like really slow. But really slow, but also really heavy. Now here I'm talking about light and fast.
You say fast, roughly what speeds are you?
So I'm still talking about maybe, so here for these fast dark matter, I was talking about 0.1 times speed of light. Here maybe I'm talking about between 10 to the minus 3 times speed of light to 0.1 times speed of light. So within that range. Yeah, and I'll explain why I'm looking for these types of particles. Now, bear in mind that for the neutrino experiments that I had, the recoil rates that I calculated were just simply this calculation. And this is really simplistic. It's not wrong because it hinges on the fact that here I'm looking at the effective number of electrons. So the dark matter is so fast that it's literally looking at the electrons like as if it's a free particle. Even though that we know that electrons in atoms are not free, right? They're bound to atoms, right? Now the dark matter is moving that fast that it essentially doesn't care. So, but when I move to smaller or less fast dark matter, slower dark matter, I really have to now probe the atom. Now, because remember that in a xenon atom, for example, I have electrons that are closer to the nucleus, which we call K-shell electrons. I have electrons that are in the second level, third level, and then the outer shell electrons, right? Now, the dark matter, if it's slow moving, can come in and only ionize the outer shell. So it can kick out the outer shell electron. Maybe it has enough speed for that. But if these fast dark matter particles can actually penetrate deeper into the atom, closer to the nucleus, and kick out those other electrons. And so this is something that we have to take into account in these calculations. And the reason we're studying this is that a lot of people actually miss this point, that these things are actually really important to look at, especially when you're looking at relativistic or semi-relativistic. And the thing to take into account here is the ionization form factor. And ionization being the fact that I'm kicking out an electron and looking for that electron, that ionization signal in my direct detection experiment. And so the reason we take these into account as well is that bound electrons already, without interacting with the dark matter, have some negligible momentum dependence inside the atom. And that electron, that wave function, sorry, that form factor takes that into account. And it says that if I just take any electron, I can calculate its bound state wave function, right? And now I have some transition matrix element, and I can look at the free electron wave function. If the dark matter does not interact with the electron, I have some bound state, I have some wave function that determines its free state, and essentially these two should be the same, because I'm not perturbing the electron, right? Then this transition matrix element should not exist, because Q here should go to 0. Q is the momentum transfer. So essentially I'm saying something comes in, transfers momentum to the same, and causes it to go out, right? It's like, I don't know, if I'm coming here and in that row, I come in and I displace you, you will have to go out, right? I just ionize you from that atom, right? But if I was really, really fast, I could kick like 4 of you, right? So it's essentially the same idea. And so I have to take those into account, because if you're electrons and I come in and I want to say ionize you, those guys are screening you. They say, no, hold on a second, you have to go through us to get to heaven. Okay, so those are the things that we have to take into account in that calculation. And really, typically in these calculations, there are ways. The simple thing to do is to assume that the outgoing wave function, the outgoing electron wave function, is just a plane wave. And I don't have to think about it. It's just a plane wave that is going out. I have some transition matrix elements. I have the bound electron wave function, and I can calculate this easy peasy. But I haven't taken into account all those atomic factors that I was talking about before, like the screening effect, the fact that I have a different dark matter interaction with the electron, either scalar or vector or whatever, which is actually taken into account by this ionization form factor here that I calculate, but not assuming anything about the wave functions here through this quantum mechanics interpretation. Essentially, what I'm saying is that I'm just going to solve the Dirac Hamiltonian, input the effects in this potential, like the fact that dark matter could be interacting through some new scalar force, vector force, blah, blah, blah. I have some screening interactions, the screening effects into that. And I can get an effect from that, the ionization form factor. I'm going to go really quickly through this. So here, this is ionization form factor as a function of momentum transfer. And momentum transfer here, you can just think of as m times v. Okay, it's mu times v, but think of it as the mass times the velocity. And at low momentum transfers, remember again, at zero momentum transfer, I'm not really doing anything, right, to the atom. I'm not perturbing it that much. But at really high momentum transfers, the dark matter is actually going really deep into this atom, right? And those, you can see the difference between these two. So the dashed line is the plane wave ionization form factor. This one is the ionization form factor that takes into account everything. And so we see much difference at this point over here. And so that means that we could be doing wrong physics in this case. And so what we find is that if I have a vector mediator with a fermion dark matter, and I compare the plane wave and the relativistic ionization form factor, I see some sort of difference when plotting this these bounds. Okay. I don't see that much of a difference here because that integral that I didn't mention is actually quite complicated. But once I do pseudoscalar mediator or different type of mediator, now here I'm saying dark matter interacts with us through some sort of other force that is not a vector force. It could be a pseudoscalar force, for example. Then I have a big difference between this. So these ionization form factors are actually really important for these kind of interactions, telling us, then they could give us information about what particle physics model actually goes into that sort of interaction. Whereas in principle for WIMPs, we can, but not necessarily that easy. Okay, so I'm really excited about this research because I think it opens up a whole new world of possibilities, some of which I've shown in this talk. And my interest really is the cosmological and astrophysical signatures that we can get from these types of models. So these multi-component models, like what are the bonds from or signatures using cosmic microwave background searches, big bang nucleosynthesis, stuff like this, really early universe cosmology. And yeah, are there any UV complete models? Like, could string theory tell me about a model that could give me these type of signatures? Those are the things. Thank you.
Any more questions? Yeah.
Is there a reason to prefer these models over axions or LSPs or anything like that?
No, and this is the thing I should stress is that it doesn't replace any of those. It's a parallel search to all of those. So like, I think axions are really exciting area of research right now, because not only terrestrially but also cosmologically and astrophysically we have a lot of data that could constrain axions. In terms of LSPs, my taste is I don't really. It's like it's heavy LHC physics that it doesn't excite me.
LHC is light superscript.
Yeah. So but you can have them being at a TV state. So those are the things, but these are really important physics questions to think about. I think the mistake that we make is to say supersymmetry is ruled out. I'm going to work on something else. I don't think it's ruled out. There's a lot for us still to do with those things.
Any more questions?
From this type of model, indirect signatures, essentially the indirect signature is, so if you can think about this as an indirect direct detection of dark matter, right? The indirect signature is this here, right? I'm annihilating A's into B's, right? And that's my, usually, if B was a standard model, typically you would say this is an indirect detection signal. But really, this is still a dark matter. So I'm indirectly detecting B through a direct detection. Yeah. So in fact, the paper that first came out, I didn't invent this, but the first paper that came out was by this group over here, and they called it indirect detection of dark. Yeah, so the masses that we have here, so if I remember correctly, what we chose here, so for example, here I have a 15 MeV dark matter mass, and the B particle is like, what, 100, it ranges from 10 MeV to 100 to what, 100 GeV. Yeah, so it's really light, really light. Oh, if the electrons interact with each other. Yes. Yeah. So those I think are really, this is like a 4 Fermi interaction. The bounds of that are within the current experimental bounds. So it should be like really high in the parameter space, and that would be there would be stronger bounds from like direct probes of these mediators. Yeah, that's the point.
Okay, I think we can end here. Let's thank the speaker again.